3 of our lecture about the different sources of internal variability in the climate system. And the one I want to talk about now is the phenomenon that you probably are somewhat familiar with from other classes about El Niño and La Nina. Now, again, breaks my heart a little bit that we don't offer the tropical meteorology / tropical climatology course as much as we used to, because we spend literally like a quarter of the course on this phenomenon. And in fact, you can go to other schools and find entire courses on the phenomenon of El Niño and the Southern Oscillation, or El Niño and La Nina. We'll get to that terminology in just a little bit here. But it kind of breaks my heart that unfortunately we have to kind of rush through a huge topic like this. But to kind of frame how this is so important to interannual climate variability, understanding and predicting what's going on with climate and climate change would be a whole lot easier if, left to its own devices, every year had globally or regionally had the same average temperature, or the same average rainfall, or the same average wind at some particular location. If, like, you knew that every year in Omaha the average temperature was this much, and the average rainfall, and we just kept getting that same amount. But of course that is not at all the way it works. There's a great deal of interannual variability in the climate of any location. Interannual, as in occurring from one year to the next. Interannual variability. You know that some years are warmer, some years are colder, some years are wetter, some years are drier, and so on. We describe that as interannual variability. Just to illustrate that, here on the left panel here I have average January sea level pressure around the world, and over here on the right, excuse me, I happen to have just January 2015. And they certainly have some similarities. I mean, there's important ways in which January 2015 does look like an average climatological January, but with a little bit of inspection you can see how there are ways in which they are different as well. And some years will be quite different and some will be less, and this particular analysis just happened to be something I had on my hard drive. It happens to be pressure, but we could have done it with any kind of meteorological variable. We could have talked about average temperature, we could have looked at rainfall, or we could have looked at wind speed, or whatever, and we would have seen that any given year its January does not look particularly that much like the average January, and the January of one year doesn't look that much like the January of a different year. I mean, there's a great deal of interannual variability in the climate system, and that's a fascinating phenomenon that was actually a real challenge in the history of atmospheric sciences and climate sciences to come to understand what actually causes interannual variability in the climate system. And it could have been any number of different things, and they have all been studied very rigorously. You know, like it could have been some kind of forced climate variability, like maybe there was interannual variability in the amount of energy being given off by the sun. Turns out that's not the case, but it could have been. It could have been changes in like the physics of how the atmosphere works. I mean, you don't need to know this particular equation. It happens to be a form of the vorticity equation, which is part of the 7 primitive equations. It's a highly simplified form of that terrible equation. A priori, we had no particular reason to think that those laws were immutable. Maybe there's changes in the relative importance of different laws or something. Turns out that's not the case, but it could have been. And that could have been why there is interannual variability in the climate system. Or it could have been that there's just some kind of weather cycles in sort of the tinfoil hat sense of the word, where, you know, somehow or other, for reasons that only people who run certain AM radio shows know, there's like cycles to the climate. Again, we've studied those things to great extent, and we know that that's not the case, but it could have been. It could have been. But it turns out that the single largest source of interannual variability in our climate system is a purely internal variability of the climate system. It's that phenomenon known as El Niño and its opposite La Nina. In case you didn't know, they are opposites of each other. They are two different patterns in the ocean atmosphere climate system. I don't remember where I got this particular dictionary definition here. It said that El Niño and La Nina are a pattern in which ocean temperatures in the eastern tropical Pacific, like off the coast of Peru and so on, are either unusually warm or unusually cold for a period of approximately 1 year. And then the change in this surface temperature ends up setting up a pattern of weather anomalies worldwide. El Nino is going to turn out to be the pattern where it is unusually, the sea surface is unusually warm off the coast of South America. La Nina will be the word we use for this pattern where the water is unusually cold off the surface of, off the coast of Peru and so on. All right, so here's a little bit of kind of an insight into how all this was originally described. This phenomenon of El Nino, La Nina, etc., where it's kind of tied to our ideas of what's going on in the ocean, actually comes to us from oceanography. Oceanographers with their, late 19th, early 20th century voyages of exploration and so on, were the ones who first found this aspect of the phenomenon, where there were these strange changes going on in the water temperature distribution across the Pacific. But at the same time, early atmospheric science and climate studies, using data that was coming in from all around the world during the era of exploration and so on, was discovering that there was an atmospheric thing going on, where there were worldwide changes in the weather patterns on the scales of interannual variability, and this came to be known as the Southern Oscillation in the world of climate science, and they're the same thing. They just were being discovered by two different communities. Oceanographers were calling this El Nino and La Nina. It's a complicated etymology as to why they call it that. And atmospheric scientists were calling it the Southern Oscillation. Again, it's kind of more of an age of exploration thing as to why they were calling it. But it was being discovered twice, kind of by two different communities. And therefore, the correct climate science, modern, interdisciplinary kind of term for this phenomenon is El Nino and the Southern Oscillation, or ENSO. That kind of correctly reflects that the climate is a coupled system of the ocean and the atmosphere. The fact that we kind of have chosen to stick with the word El Nino is more just sort of a cultural thing, okay? The right word is actually ENSO, but you'll see I use the word kind of kind of inconsistently there. All right, anyway, let me show you what an El Nino looks like in the ocean perspective. Here happens to be a map that I made of the sea surface temperatures across the tropical Pacific in January. It's a 30-year climatology that I happen to have on my hard drive. Okay, and you can see that there's interesting phenomena going on. In general, the Western Pacific is warmer than the Eastern Pacific, and there's all kinds of interesting things going on. And again, the tropical course would be a wonderful resource for you to understand what's all going on here. But interestingly, it doesn't always look like that. There is interannual variability in the sea surface temperature distribution. And if I happen to pick, say, January of 2016, which was a big El Nino year, you can see that at that time there's actually a rather significant difference in the temperature distribution across the Pacific Ocean. It's actually a whole lot warmer in the Central and Eastern Pacific than usual. Think about the amount of energy it takes to warm up an area of the ocean roughly the size of the continental United States by several degrees Celsius. I mean, this is an astonishing change. And it doesn't happen fast. It takes, on the order of months to like a year to get to this condition. And it's going to stay that way for about a year. And then with time, it'll change in reverse and become unusually cold in that part of the world. In fact, if you take the difference between the January 2016 sea surface temperatures and the climatology, you get the climate anomalies. You get the difference. How unusually warm is it in the tropical Eastern Pacific, and how unusually cold is it in other places? And if you do that, if you take a look at the anomalies of sea surface temperature across the Pacific in January 2016, you see this huge temperature anomaly across the eastern and central equatorial Pacific. That is a sea surface temperature anomaly that is very typical of El Nino. Again, think of the vast amount of energy this involves to warm the ocean, 2, 3, 4 degrees Celsius. This was not by any means the biggest El Nino ever. Sometimes it's more than 5 degrees Celsius. That's like 9 Fahrenheit. Think about the amount of energy it takes to make the ocean 9 degrees Fahrenheit warmer over an area that big. Notice it's along the equator, it's in the Eastern Pacific, and so on. This is all very typical of what we call El Nino. And these sea surface temperature anomalies are being driven by interesting internal variability of the ocean. There's interesting Kelvin waves, you don't need to know that term, going on internally in the ocean at great depth that are just about the physics of how fluids move that redistribute heat across the Pacific Ocean. It's just an internal climate variability. It's just something the climate system, it's a fluid mechanics. It's not being driven by greenhouse gases. It's not being driven by, the sun isn't giving off more energy during an El Nino year than during a La Nina year or anything like that. It's just the internal variability of the climate system. And so, in this case, we would say that January 2016 was part of an El Nino event, very typical looking, fairly average El Nino event. Those sea surface temperatures have an effect on the atmosphere that sets up, because the ocean and the atmosphere are coupled, and so changing the distribution of the water temperature changes distributions of evaporation, changes distributions of conduction of heat from the ocean into the atmosphere and so on, sets in motion thunderstorms in places, for example, the areas with the higher sea surface temperature anomalies tend to be then areas where unusual amounts of thunderstorm activity happen and unusual amounts of rain happen. If you remember things from Introduction to Atmospheric Sciences, that's going to be where unusual amounts of latent heat release happen. It starts becoming a very, very complicated, strange climate anomaly into the atmosphere as well. And for that matter, you can, a few years later, get the opposite to happen. For example, this happens to be January 2011, which had unusually cold water temperatures across the equatorial, central, and eastern Pacific. And as you can see, it's like 2 degrees cooler than normal, which is, like 4 Fahrenheit colder than usual across an enormous area, like the size of North America. An enormous amount of heat has to have moved for this to have happened. Again, it's just driven by the internal variability of the Pacific Ocean. It's purely being driven by, internal Kelvin waves on the thermocline and all kinds of cool stuff that you can learn great deals about if you take the tropical course. But the idea that we have made a massive change into the distribution of the water temperature ends up having big consequences for like the flux of latent heat and sensible heat, that is to say evaporation and conduction of heat, all over the equatorial Pacific. This ends up being very typical of the weather pattern and the ocean pattern that we call La Nina. So January 2011 turns out to be part of a La Nina event. If we just sort of define a chunk of the Central Pacific, oceanographers use this term Niño 3.4. It's complicated how they came up with that name and so on. But if you just sort of average over the water temperatures over that part of the world, what you see is that there's a pattern of warmer than normal conditions and colder than normal conditions that happen from year to year. There is interannual variability of the water temperature across the Central Pacific just due to internal variability of the ocean climate system. And there's all kinds of things we can learn by looking at it. Here's, by the way, that was only, about a 17-year diagram here. This other one here is longer. It's about 70 years. If you actually do the analysis of these events and so on, what you find is that typically the El Nino events last about a year, and La Nina events last about a year. Sometimes it's as short as like 9 months. Sometimes it's as long as like 2 years. But they're approximately an annual event, an annual scale event, and it takes about 4 years to go from one El Nino to another. So like if you have an El Nino that happens in 1983, one of the biggest El Nino events, then by about 1987, about 4 years later, you'll get the next El Nino event, and then by about 1992, you get the next El Nino event, and so on. They're averaging about 4 years apart. Longer climate records than this show that sometimes they're as little as 2 years apart, sometimes they're as much as like 7 years apart, but the internal variability of the Pacific Ocean is a fairly predictable thing, averages about 4 years, and most of the time between one El Nino event and the next El Nino event, there'll be a La Nina event where the water is unusually cold. Not always, but most of the time. And again, maybe that's a little easier to see on the color diagram here, how it goes from a cold water to warm water, to cold water to warm water, and so on. It's a purely mechanical physics of the ocean thing, not being driven externally by volcanoes or greenhouse gas emissions or anything like that. Notice that some of these El Nino events and some of these La Nina events are a whole lot stronger than others. I mean, the 2016 El Nino was a pretty big El Nino. The water was pretty warm. Average over the whole Niño 3.4 domain, the water temperature was about 2 degrees Celsius higher than normal. Some El Ninos are more like, 0.8 of a degree average over that big region and so on. The biggest El Nino in terms of sea surface temperature anomaly we ever had was in 1982 and 83. But, there's quite a range in the sizes of it. There's also variability from one El Nino event to another. Well, this is all fascinating. It has a lot to do with what's going on inside the ocean. We could, take my tropical class. We'll have lots of fun talking about all the different kinds of processes happening on the thermocline and on the deep ocean and in the shallow, the mixed layer and so on that makes this happen. We can't do that in one part of one lecture of this course. But how we have to tie this, we have to couple this to what's going on in the atmosphere and ask, how is this affecting the weather around the world? Well, remember how I told you that those areas of warm sea surface temperature anomaly turn out to also be where a very large number of thunderstorms happen. And those thunderstorms are going to set up patterns of troughs and ridges downstream from them. This is a complicated idea that there's no way we can get to in one lecture of one 500 level class. But it sets up what's called a Rossby wave train, a pattern of troughs and ridges downstream. In much the same way that in a real stream, a rock in the stream sets up a pattern of waves downstream. It's sort of a standing pattern to the waves, right? As the water flows over the rock, you get those kind of waves downstream. In exactly the same way, these unusual thunderstorms that occur during El Nino, they're not unusual in that they're weird thunderstorms, they're in a weird place. There are not normally a lot of thunderstorms in the tropical eastern Pacific, yet now there is. They set up a pattern of troughs and ridges around the world. Now I tried to illustrate this. This comes from a completely different context, but a pattern of troughs and ridges. Imagine that like the red line on this map here was the jet stream. The thunderstorms in the tropical eastern and central Pacific set up a pattern of troughs and ridges. You remember how the troughs are kind of that dip in the jet stream? I hate that term, dip in the jet stream, but it'll apply here. And there's a pattern of ridges, kind of that where the jet stream is going to the north and then it makes a right turn back to the south. There's a pattern of these troughs and ridges that get set up. And that pattern doesn't move. Okay, just like when there's a rock in the stream and downstream from it you get those waves. And they are standing. This is a standing pattern of troughs and ridges. Very different than the troughs and ridges that affect our day-to-day weather now. If it's not an El Nino or a La Nina year, most of the troughs and ridges that affect our day-to-day weather are migratory, to use the correct term from like meteorology. Troughs and ridges progress, usually from west to east. These are going to be standing features. We're going to be persistently under a ridge in the western United States. We're going to be persistently under a trough in the eastern United States, and that has important consequences for the weather of those parts of the world. It's going to be unusually wet and stormy in the eastern United States. It's going to be very dry across like the Intermountain West and so on. And there's a pattern like this that sets up in the southern hemisphere. There's a pattern, we get excited about the one in the northern hemisphere. It has a cool name. It's the PNA pattern, or the Pacific North America pattern. Meteorologists learn all about the cool business of the standing pattern of troughs and ridges known as PNA. But it really is an El Nino thing. And you'll have a different pattern of those troughs and ridges that becomes a standing pattern in La Nina conditions. And both of them kind of lock in certain weather anomalies, changing everything. I mean, they change where cyclogenesis happens around the world. Cyclogenesis, the process of creating cyclones. It's going to change the storm tracks, the parts of the, pattern places where preferentially winter storms are passing or whatever. It's going to change where air masses form. It's going to change where air masses move. It's going to change preferentially like where hurricanes can generate and how they can progress and so on. There are huge changes across the Atlantic Ocean and the distribution of hurricanes and so on due to El Nino and the Southern Oscillation, or ENSO. Worldwide, you could look for signals all over the place. Turns out this business of El Nino and the Southern Oscillation, or El Nino and alternatively La Nina, is the main source of internal climate variability in our climate system, which of course makes you wonder how we're messing with it, right? Increasing interannual variability of climate would be a spooky thing, potentially with very serious implications for like society and so on, in terms of like how weather is affected and how it impacts society and so on. yeah, one could start thinking about, gosh, if we're changing temperature distributions in the ocean and we're changing, distributions of troughs and ridges in the atmosphere, oh my. Can you see how our forced climate changes by things like changing distributions of greenhouse gases and aerosols could be making changes to El Nino and the Southern Oscillation? Well, clearly that's in the domain of the IPCC to look into such a thing. And it was a challenge. Because it turns out, historically, like if you go back a decade, or 2 decades, or 3 decades, we had a real problem. Coupled ocean atmosphere models used to just be absolutely terrible at simulating El Nino. I mean, if you used the observed ocean temperatures during an El Nino event and just used them in a not coupled, in a one-way coupled way, where you just said let the ocean change the distribution of thunderstorms and latent heat flux and sensible heat flux in the atmosphere, oh, they work just fine. But if you coupled them in a two-way way, where you let the atmosphere create ocean currents, and you let ocean currents affect the atmosphere, you didn't get anything even remotely looking like a realistic El Nino. This used to be a huge problem. It used to be one of the central challenges in climate modeling, just to figure out how to get coupled models to come up with realistic El Ninos. And the good news is we seem to be able to do that now. Now, state-of-the-art climate models, if you just set them in motion with constant boundary conditions of certain amount of greenhouse gases and certain solar flux and so on, you let them run, they get fairly realistic looking El Ninos in their coupled ocean atmosphere climate system. Every simulated 4 or 5 years you get a warm event, and every, between them you get a cold event. It looks good. This is a problem that science dedicated resources to solve, and we seem to have done it. By and large, climate models can do this now, and what the IPCC Fifth Assessment Report actually says is the realism of the representation of the ENSO cycle in climate models continues to increase, and models simulate ongoing ENSO events and their variability in the future. The climate models can't predict that the year 2076 is going to be an El Nino year, but they can simulate that, like in the 2070s, we continue to see El Nino events and La Nina events spaced about 4 years apart, lasting about a year. They look realistic. And that tells us something important about where the climate system is going. It tells us that climate models are giving a strong reason to believe that there's no particular reason to think that the ENSO system is going to somehow stop or fail. Even under a fairly wide range of different RCP forcings, where we apply different anthropogenic radiative forcings up to and including 8.5 watts per square meter, which is way on the high end, we continue to see El Nino happening in the future. That's probably for the best. It's probably for the best in terms of our ability to adapt to climate change and so on, that El Nino is going to continue. It's part of the variable. We're not throwing the ocean into a new climate regime where it is not able to produce interannual variability in the same way. That's, in the world of climate science, that's probably good news. Another thing that they tell us in the IPCC report is that, therefore, there is high confidence that ENSO very likely remains the dominant mode of interannual variability for the future. And due to increased moisture variability, the associated precipitation anomalies and precipitation variabilities on regional scales is likely to intensify. In other words, the parts of the world that are unusually wet during El Nino, like the southeast United States, are probably even going to be wetter. Or Peru. Peru is very wet during an El Nino event. It's going to be even wetter, just because the atmosphere is going to be holding more moisture in the future. This tells us too, then, just to kind of paraphrase, that El Nino is going to continue to be an important part of our climate system, regardless of what our radiative forcing moving forward is. El Nino will continue to be providing an important source of interannual variability of climate due to internal processes, for the foreseeable future. Now, what does that actually mean, for individual regions and so on? The IPCC report gets a little bit vague here. It says, however, natural modulations of the variance and the spatial pattern of ENSO are so large in the models that confidence in any specific projected change in this variability into the 21st century remains low. In other words, we're talking again about that variability between one El Nino event and the next. When we look at the record, we see that some El Nino events are much bigger than others. And some are much smaller, or sometimes they're farther apart, and sometimes they're in time. Sometimes they take longer to happen, and sometimes they take less time. Sometimes they happen a little farther to the west than other times, etc. There's quite a lot of natural variability from one El Nino to another. And the models kind of make a mess of that. They all have very subtly different ways of depicting El Nino in these couple of models. I mean, it's only in recent years that we've gotten them to do it at all. So it's not surprising that the models have surprisingly different looking El Ninos in terms of how strong they are, how often a strong El Nino happens, how often a weak El Nino happens, what fraction of El Ninos are strong, what fraction of El Ninos are weak, and so on. There's sufficient variability from one member of the ensemble to another that the IPCC says that we're kind of, the certainty here is low. We in terms of like what the actual impacts will be as to like how does one El Nino look different from another in the future. The models are all kind of saying slightly different things. The models are in disagreement about what this means for like downstream impacts and so on. But we know El Nino is going to continue to happen. We know it's going to continue to be an important part of the climate system. All right. You know, that's actually an amazing result. We're worried about the collapse of the Atlantic meridional overturning current. We're worried about the possible collapse of the West Antarctic ice sheet. Surprisingly, the single largest source of interannual variability in our climate system, namely El Nino and the Southern Oscillation, seems to be fine. At least for the period of the next, the rest of the 21st century, the models seem to indicate that we're not fundamentally changing that source of interannual variability. That's actually kind of amazing. All right, maybe we're making it a little wetter, maybe we're making it a little drier in some places, maybe we're slightly changing the positions of troughs and ridges and so on, but the fundamental source of interannual variability in the climate system, due to this internal variability that we call El Nino, looks like it's going to stand. All right, before we move on to our fourth part of the lecture here, let's answer a couple quick questions. Question 7. During an El Nino event, the sea surface temperatures, or SSTs, in the eastern and central tropical Pacific are usually A, cold, B, warm. That should be pretty straightforward. Make a choice from those two options and get a little feedback before you move on to question 8.